Hi, I'm Robert Kollman. I'm a Senior Applications Manager at Texas Instruments. Welcome to Power Tips. Welcome to Power Tip 34. In this Power Tip, we will design a simple isolated bias supply. This isolated power supply will be used in systems that require isolation and relatively low power devices. These devices might be a microcontroller, they might be an RS-485 interface, or they might simply be a digital isolator. Typically, these kinds of systems use a 3.3 or 5 or plus or minus 15 volt output, and typically they'll run on a 3.3 or 5 volt input. But sometimes you'll see 12 or 15 or 24 volts. Typical output voltages are 3, 3, 5, and then plus and minus 15 volts. And many times these type of systems are fairly low power, only needing 1 or 2 watts of output power. Here's a circuit that we developed for these kind of systems. Actually, the IC was specifically developed for this particular application. It's a buck regulator. It has a 3.3 or 5 volt input applied to it. It has a totem pole power stage that's connected between VN, the phase node, and ground. And the control IC controls the conduction of the MOSFETs in the totem pole to set an average voltage, and the output of the filter voltage is monitored and sets the duty factor on the control IC. That's kind of a typical buck power supply. What we've done in this system is we used a coupled inductor to generate our isolated output. And so rather than having just a buck inductor, we have a buck inductor with a secondary on it also. And the secondary feeds a diode. The diode conducts when the input to the filter is low. And when the input to the filter is low, the voltage across the primary of the inductor is equal to this regulated output voltage. And that is detected by this diode in the secondary, which rectifies the voltage from the inductor and then provides it to the capacitor, which filters it. And so the output of the power supply is pretty well regulated by regulating the voltage across the inductor. You have to be careful with your choice of the values of the leakage in the coupling inductor. Just like we saw in the SEPIC in a previous power tip, you can create large circulating currents within your system if you allow the leakage inductance to get too small. Here in this slide, we're showing 3 simulations, and the simulations were all done with the same primary inductance on the coupling inductor, and then we varied the leakage inductance. And you can see we varied it from 10 nanohenries up to 100 nanohenries up to 1 microhenry. You can see with the 10 nanohenry case, we end up with a significantly higher peak current in the secondary of the inductor than we do with the larger inductances. And this will translate into high RMS currents in the circuits. So here in the little chart on the right, we have the primary RMS current with the different inductors, and we see the diode RMS current with the different values of leakage inductance, and you see the peak current in the output rectifiers with different values of leakage inductance. And with these higher values of current, with the very tightly coupled inductor, we'll find that the efficiency is not quite as good. Now, this circuit provides pretty good load regulation. It is not perfect in that you have some voltage drops in your secondary, your circuit, such as the output rectifier and the winding resistance of the inductor that degrades the regulation. And so what we have done here is provided a typical kind of regulation that you'll see with the circuit. On the x-axis, we have output current, and then on the y-axis, we have output voltage. This was meant to be a power supply for a 5-volt system. And you can see that once we got above about 10 milliamps of current, the regulation on the 5 volts was within 5%, and it remained within 5% all the way out to about 300 milliamps. So this is a nice, simple circuit. It's low cost, but it does have the downside that the regulation isn't particularly good. You will be able to get 5% regulation over the loads with the circuit that we showed. We believe that you can improve the regulation with the addition of synchronous rectifiers and we're in the process of verifying that. Efficiency is good with this circuit. We typically achieve about 80% efficiency with a 5-volt output at 2 watts. And the other very good thing about this circuit is that it can be used for high voltage isolation. We've developed applications where we deliver more than 3750 volts of isolation between primary and secondary circuits. Well, thanks for the attention for this power tip. You can find more power tips on the EE Times website. Just search on power tips and you'll find them. Or you can click on the link to all articles in the description section of this video. Thanks.